let's see if you can spot when that happens. Okay, so last time it seemed that people were both very interested and also a little bit confused about this idea of spurions, okay? So I'm going to just give a little recap from a slightly different perspective, okay? So that might help a bit for some of you. But then I'm also just going to start doing a bunch of examples, and I think as usual, once you start seeing examples, hopefully that will make things more clear and so on, okay? But again, please do interrupt me, because I would love to have a chance to not be talking and just let you guys talk to me. All right, so I'm going to talk about spurions. I'm just going to make some general remarks from a general point of view that is a little different from what I said, okay? So we're very used to the idea that a theory is defined by a path integral, okay? So I'm going to be pretty schematic. I just have some fields, okay? And then I have some action, okay? But the action, I can think of it as not just depending on the fields, but it also depends on the coupling constants and masses, right? Those are parameters in the action. They're terms in the action. They involve G and M and so on, okay? And you may say, well, these are completely different kinds of things because this phi is a function of space-time. It's a field. These are just numbers, okay? But one way to think about spurions is I can say, well, if I can solve this problem, okay, it's not so very different for me to think about solving the problem where I just promote every parameter to a field, okay? But notice that I'm not integrating over the possible values of G. I'm only integrating over the fields, the dynamical fields, right? Okay? So you can think of these coupling constants as some background fields that just happen to be constant in our world, okay? But as a theorist, I can think of them as being fields, okay? That's not a very big leap, okay? Now, why would I want to do that? Okay, well, let's just ignore these as parameters, okay? One of the things that you're supposed to learn when you're a particle physicist is if somebody gives you an action, you're supposed to immediately look at it and say, what are the symmetries of this action, right? Does this action have any symmetries? Is there a phi goes to minus phi symmetry? Is there a U1 symmetry? Is there, right? Okay. Now, do the same exercise with these fields included, okay? All right? Now that means that I'm allowing more symmetries because I'm allowing them to act on these fields, okay? That's what spurion analysis is. The basic idea is just that the more symmetry, the better, right? If I have more symmetries, I can make more predictions, okay? Because symmetries are very powerful. So if I have them, I want to know about them, okay? So this is sort of just another way of thinking about what spurions are, and it sort of tells you what the general idea is. The general idea is that I look for all the symmetries of an action, including the ones that act on the parameters, okay? And so now I'm going to just start doing some examples of this to show you why this is useful. Okay, so any questions on this? Okay, so the example I'm going to do, it was already anticipated last time, was the effective so-called chiral Lagrangian for QCD. This is really the effective theory of light mesons like the pion. So to set the stage, let's focus in on QCD. And so what is happening, okay, in QCD, we have some heavy quarks. We have the bottom quark and the charm quark. We also have the top quark. It's way above, way up on this axis somewhere, okay? And then not too far below the charm quark, QCD gets strong, and we have the QCD scale at around a GeV, okay? And then down here, we can't really talk about quarks anymore, right? Because we have strong interactions, we have mesons, baryons, things like that, okay? But in terms of the fundamental parameters of the standard waddle, m up and m down, the quark mass parameters in the standard model are believed to be around 5 GeV. And part of the story is, how do we know that? Okay, that's going to be part of this story, okay, because we certainly don't measure a quark at 5 GeV. And then there's the strange quark, which is, sorry, not GeV. Why doesn't somebody stop me before I say something stupid? MeV, 5 MeV, okay, so it's way below a GeV, okay. The strange quark mass is around 200 MeV, so it's not that far below the QCD scale, okay. But it turns out to be useful to think about these guys as being much smaller than lambda QCD. And these guys, even though the charm quark mass is what? Something like 1.3 GeV? I forget. What is the charm quark mass? Yeah, something about that, okay? So even though this is not very far from this, it's useful to think about this to be as being much larger, all of these guys to be much larger than lambda QCD, okay? So I wanted to start with this to just make it clear that this is not the cleanest thing in the whole world, okay? If we lived in a world where the charm quark was much, much heavier and the strange quark was much, much lighter, everything that I'm going to say would be much more accurate, okay? But it turns out, as I'm going to show you, that it's very useful to think of things in this way, in this hierarchical way. You can think about it as, you know, doing an expansion, and we'll see how fast it converges, okay? It's a systematic expansion, and it actually works quite well, okay? Okay, so with that in mind, I'm going to write down the Lagrangian of QCD here, okay? Below the quote-unquote heavy quark masses, I've integrated them out already, okay? But above the scale lambda QCD. And then I'm going to try and figure out what the effective Lagrangian is down here, okay? And I'm going to be able to make a lot of progress using this sort of spurion analysis. So let's start with QCD. What does QCD look like? Okay, well, QCD has a, kinetic term for the gluons, which I'm going to just write like this. Okay, then it has a quark field, and there are three flavors of quark, U, D, and S, right? We have three, so I'm going to collect them into a multiplet like this, okay? And these are Dirac fermions, okay? So I have a kinetic term for all of my quarks, which I just write like this, okay? And then I have a mass term, okay? And I'm writing it this way because, for me, little mq, okay, is a 3x3 matrix, which is diagonal, okay, because I done diagonalized the masses, the quark masses, which I can do, and we'll talk about that more later. And this is it, okay? This is the whole thing, all right? So now let's do our exercise. Our spurion exercise is we're supposed to take this Lagrangian and find all the symmetries that it has, okay? So first, if we don't think about this as a spurion, we have our old-fashioned, old way of doing things. Then if we look at this thing here and we do the exercise of saying what are the symmetries of this, we would say that there's a U1 that acts on left-handed quarks and a U1 that acts on right-handed quarks, okay? All right? And so that's because, right, as you know, this thing here is a separate kinetic term for left and right-handed quarks, right? Okay, and so this is invariant under rotations of left and right separately. Sorry, but this thing here is breaking that symmetry, right? This is breaking that symmetry. So in fact, all we have is a U1 of quark number. That's the only symmetry we have, which is basically baryon number, right? That's a third of baryon number. So that's not very interesting, okay? It's not very useful, okay? On the other hand, if we look at things from the spurion perspective, okay, now this is important. Now you see that I can rotate left and right-handed quarks independently, okay? And if I look at this thing right here, what does this look like? It looks like QL bar MQ QR plus Hermitian conjugate, okay? So notice I'm allowing MQ to be complex, and I'm not thinking that it's equal to this. I'm thinking it's some background field where only at the end of the day, after I do my path integral, when I evaluate physical quantities, only at the end of the day am I going to set it equal to this. So now what symmetries do I have? I claim now I can take QL and rotate it by a full U3 matrix, which I'm going to call L for left-handed, and then I can take QR and rotate it by a complete 3x3 unitary, this is U3R, this is U3L, and so I have a U3L cross U3R symmetry, okay? That is a symmetry of the kinetic term, right? You can see that. It's not a symmetry of this, but it is if I allow M to transform. So how do I make M transform? Who can tell me? What do I write? L, yeah, this is probably what you meant. L, MQ, R dagger. Okay, so now I have to think of MQ as a general complex matrix, okay, if I do this, and only at the end of the day I'm going to set it into this. But look how much I've gained. I've gained a ton of symmetry, okay? All right? Okay, so now there's some shenanigans now, okay, because so this symmetry right here, U3L cross U3R, you know that U3 is SU3 cross U1, right? So I can write this as SU3 left cross SU3 right cross U1 left cross U1 right, okay? But it turns out that this piece has an anomaly, okay? And actually, it's very possible, now that I think about it, that I will discuss this anomaly in more detail later when we talk about the strong CP problem, okay? But for now, let me just tell you the facts. So the fact is that this is broken by an anomaly down to the U1, which is just that U1 that I called U1Q before, right? Okay? All right? Okay. Then I'm going to tell you some more facts about QCD, which is that one of the things that we believe happens when we go below this scale, okay, so when QCD becomes strong, it actually spontaneously breaks this symmetry, okay? And so what happens is that I get a vacuum expectation value for a quark condensate, Qi, Qj. So these I and j's run over UDS, so this is a 3x3 matrix, okay? And in the limit where the quark masses go to 0, okay, so remember, I'm supposed to be thinking about the quark masses as being small compared to lambda QCD. So as a first step, we want to understand what happens when they go to 0. And the claim is that this gives me a non-zero condensate proportional to lambda QCD. And in this flavor space, it's just a Kronecker delta, delta ij. Okay? Now there are phenomenological models for this. We can understand this from lattice QCD, and we can also understand this is true because it works. It describes what we see, as we're going to find out. Okay? Okay, so great. So we have to incorporate this fact into our low-energy effective theory, right? And in fact, it tells us what kind of low-energy theory we have, because in the limit MQ equals 0, this means that, so this thing right here, you can easily see that this breaks the SU3 left cross SU3 right spontaneously down to the diagonal SU3. And so this SU3 is where L is equal to R, right? It's the subgroup where L is equal to R because this is basically, this thing transforms like this, and it's proportional to the identity matrix, so it is exactly preserved by the transformations with L equals R. So that tells us that we have Nambu-Goldstone bosons that are associated with this coset, SU3 left cross SU3 right, broken down to SU3 diagonal. Okay, this is sometimes, I can call this L plus R if you want. Okay? And this is unbroken, so it doesn't appear here in this coset. Okay? All right, now there's a standard technology for how to write down effective field theories for Nambu-Goldstone bosons. And I'm not going to be able to explain it, okay, because it would take us too far afield. But if you want some bibliography, you should, there are classic papers by Callan, Coleman, Wess, and Zimino. Okay, that explain this, okay? And there are probably reviews that are easier to read than the original papers. Actually, the original papers are very beautiful, too. So I'm just going to tell you the answer, okay? And I'm going to try to make it plausible, okay? Because we're being pheno people here, okay? So the idea is the Nambu-Goldstone bosons live in this coset, okay? And so the way we parameterize them is we parameterize them by some fields phi of x, which can be written like phi a of x Ta, where these are these TAs are SU3 generators. Okay, right? Which means there are eight of these guys. Okay, and that's exactly, you know, the number of broken generators. Okay. And the idea of Callan, Coleman, Wess, Zimino is that even though this symmetry is spontaneously broken, okay, it makes sense to ask, how does an SU3 left cross SU3 right transformation act on these fields? Okay, so the idea is that, you know, in the sort of Mexican hat or American tourist hat potential type picture, there's some space of vacua, and the pi's are fluctuations around this flat circle, right? But if in the UV you make some SU3 left cross SU3 right transformation, it somehow takes you from here to somewhere else. There has to be a consistent rule for doing this, okay? All right? So that's the basic physical idea behind Callan, Coleman, Wess, Zimino, okay? And they beautifully showed that given this idea, you can always put the Lagrangian, effective Lagrangian, in a certain very useful form, okay? That's the content of this paper. So I'm just going to tell you what the answer is, okay? And so the answer is that we define a field sigma of x, which is just e to the pi of x. So this is a local element of SU3, okay? All right? And then under the SU3 left cross SU3 right, this thing just transforms, I can just use sigma. This thing just transforms like this, okay? That's obviously a well-defined rule, okay? Because these are all SU3 elements, so this is an element of SU3, so this makes sense, okay? And the claim is that not that this is unique, it's absolutely not unique, but the claim is that any other rule that I could make up, right, that has certain consistency properties, like, for example, that you have to check that this subgroup acts in the correct way. Actually, let me just show that while I'm doing that. So what's right about this? First of all, that it's well-defined. That's always a good sign, right? It's always a good place to start. But there's another thing which I could check, which is that if I take L is equal to R, and let me call it U, so that's the unbroken SU3. Under the unbroken SU3, this thing should transform as a good old linear representation of SU3, right? And in fact, it does, okay? Because if I take the SU3 left plus right, how does it act? So sigma of x goes to u, e to the I pi, u dagger, right? But that's equal to e to the I u pi u dagger, right? By the magic, you know this thing, okay? But this is just pi prime, so that's just telling you that pi prime is transforming in the adjoint representation of the unbroken SU3, okay? So that's basically the claim is that any rule that you can cook up that is well-defined and has this property you can do a change of variables and turn it into this. So this is as good as anything else. That's the claim of Callan, Coleman, Wessamino. Okay? It's a classic paper. Okay, so, all right. So now, given all of that, our job is just to write down the most general effective Lagrangian that we can for just these fields. Okay, so I erased my diagram with lambda QCD. So here's lambda QCD. Okay, and there are 8 mesons that are light. Okay, in the limit where these quark masses vanish, it's the m pi plus minus, m pi 0, mk plus minus, and their and the neutral kaon, and its complex conjugate, and the eta. Okay, so it's the pions, the kaons, and the eta. That's 8, I hope. It's late, and I'm fried, so I hope that's 8. And they make up an octet under SU3. Okay, so, you know, back in the day, Gelman just said, hey, why not SU3? Why not an octet? And, you know, he found that it worked, okay? But now we have a better understanding of this, okay? That these are actually the light Nambu-Goldstone bosons, okay? All right, so now what is our job? Our job is now to write the effective theory for these guys, right? These guys are all contained in pi of x, okay? And if I was prepared for this lecture, I would show you the matrix in terms of these guys, but I'll just get it wrong if I write it, so you can look it up. But what is this effective theory supposed to look like? Remember I told you about this refined power counting where we can put in factors of 4 pi and so on. So this is supposed to look like lambda to the 4th g star squared, okay? And then it's supposed to be some function of g star times pi hat over lambda, okay? Del over lambda, okay? So let me explain a few things, okay? So suddenly a hat appeared here. What's that all about? Well, if you look at what I've been doing here, I've been putting pi up in the exponent, okay? Which means that pi, the field, is actually dimensionless as I've defined it. That's what it naturally is. It's an angle, right? In fact, if I take pi through 2 pi, too many pi's, I know, but it's okay, right? This is traditional. So if you take this field pi through 2 pi, you in fact go back to where you started. It's literally an angle, okay, right? Okay, but I want my scalar field to have dimension 1, so my pi hat has got dimension 1, okay? And so what is lambda here? Lambda is lambda QCD. So I'm going to start, I'm going to be tired of writing QCD all the time, so I'm just shortening it to that. That is the scale where the theory breaks down. That's just what I told you it was when we did this, okay? And G star I'm going to take is going to be 4 pi. This is a strongly coupled theory. I'm not taking large n. N equals 3 I'm saying is not large. Tomorrow I might say it's large, but today I say it's not large. And so this is it, okay? So now you have to, so if I write things in this way, right, what do I get? What was motivating this is that, for example, if I use this counting, you can see that the kinetic term, it's got 2 derivatives, 2 of these, that exactly cancels this factor, I get an order 1 thing, right? And then I get higher order terms, for example, g star squared over lambda squared, something like pi hat squared, del pi hat all squared, okay, and higher order terms, okay, all right? I claim there's always at least a couple of derivatives here, okay? And the reason is that these terms right here all have to come from some theory, okay, where the Lagrangian is written in terms of this sigma, right? And let me just remind you, the sigma has this transformation law. It has to be invariant under this. Okay? All right? And just for now, I'm just setting m quark equals 0 for now. Okay? Then what does this look like? Well, there's going to be some kind of a coefficient, okay, times, just dimensionally, there has to be a lambda squared. I'm just going to write this term down. I claim the lowest dimension term you can write is something that has two derivatives like this, okay? And the reason this works is that you can see that this thing, remember that L and R do not depend on X. These are just constant things, okay? And so the derivative just goes right through these. So this transforms like sigma dagger, and this transforms like sigma, okay, under L cross R. And so this is completely invariant, okay? So now there's a little exercise. If I expand this out, this is whatever this number is times lambda squared by dimensional analysis. And then what I see here is the first term that I see looks like d pi squared, okay, because I just get 1 power of pi from here and here. Then the next term looks like pi squared d pi squared, okay, and so on and so on. Okay, so that's why, sort of with malice aforethought, why did I write this term and not one of the infinitely many other things I could have written? It's because this is actually what I get by expanding these things. Yes? Yeah. Well, the fundamental Lagrangian is QCD. So I mean, these are both the same Lagrangian. Okay, what am I doing here? Okay, I'm a little fried, so I'm sorry if it's a little unclear what I'm doing. What I'm doing here, let me say it in perhaps a more logical way, okay? Okay, forget about this for a second. I wish I'd said this in a different order. So let me start with this, and now I think you're happy with this, okay? But then I say, oh, but this same Lagrangian is supposed to have this form, okay, which looks like this. This is what I should have said. So now the question is, how do I rescale? This phi hat is just some rescaling of phi to make these two things agree, okay? What is that rescaling, okay? It's a boring exercise, but I'm going to tell you what the answer is. The answer is that pi hat is equal to f times lambda, okay? You can call this f pi if you want, but I'm just going to call it f, but it's what people call f pi. And this thing is, and lambda over f is just my name for g star, which is of order 4 pi, okay? So this is just kind of a traditional way of parametrizing things. So that's what I'm trying to say here, okay? I'm just trying to figure out how to write things so that it looks like this refined power counting. There's a pi missing? I've got so many pi's, you want even more pi's? No, which part? Yeah. Oh, sorry. No, just times pi, right? By dimensional analysis, this is dimensionless, this is a mass. Yeah, but okay, but you're right, I was missing a pi, okay? Okay? Okay, good. All right, so that's it, okay? So once we understand that, okay, we can rewrite our rule, okay? So we can rewrite our rule as like this, as f squared times m squared times some function of, and now I'm going to write it in terms of the variables that I really want to write it in terms of, namely sigma, okay, and also derivatives divided by lambda. I'm sorry, I'm going to call this lambda. In my notes, I switch back and forth, but I'll try not to do that here, okay? Okay, and I'm leaving some room here. Okay, so I claim where sigma of x is now equal to e to the pi hat of x divided by f. Okay? All right? Everybody happy? Okay. All right, so all of this was for mq equal to 0 for now. That was our 0th order starting point, okay? But now the idea is that the quark masses are not 0, but they're small, right? They're small. So it's going to make sense to perturb in them. That's the idea, okay? And so if I go back to the QCD Lagrangian, right, I have this mass term, which is like q bar mqq in the QCD mass scale. And so what is this m? in terms of the spurion way of thinking, it's just some field that has mass 1, okay, right? And it's just some field that has mass 1, and it transforms, as we said, under SU2 left cross SU2 right like this, okay? So I claim that if you think of this as an external field, okay, it would couple, once again, with just, I claim that it would couple like this. It would couple with an MQ over lambda, okay? All right, so I'm not going to go through and show that, but the same sort of logic that tells us that if we require that, loops should be suppressed by powers of g squared over m pi squared, and derivative things should be suppressed by powers of lambda, tells me that I would expect this kind of power counting, okay? Okay? All right, so this is our starting point. This is the grand starting point, and this right here, when it was originally written down by Georgi and Manahar, for reasons that no one can understand, they called it naive dimensional analysis, okay? Which seems a really weird thing because it certainly is dimensional analysis plus. It's not dimensional analysis minus, right? But anyway, you sometimes will hear it called naive dimensional analysis, okay? And remember that lambda is of order GeV, okay? And that's supposed to be of order 4 pi f, right? That's sort of our power. So there's secretly 4 pi's in here, right, because of this, okay? Okay, so now we just do the thing, okay? So let's just start writing down terms in the effective Lagrangian, okay? So the first one is the one that I've already written down, the kinetic term, okay? So the effective Lagrangian, according to this power counting, would be f squared trace d mu sigma dagger d mu sigma, okay? All right? And now the thing is that now, if you were really doing, I'm not going to do factors of 2, but if you were, you would be basically defining this coefficient to be 1, okay? And then you would find that indeed, if you use the conventional normalization for the generators, okay, that this term would be literally 1/2 d mu pi a d mu pi a, okay? So the naive counting tells you that it's of order f, okay? But if you actually plug into this, if I make this thing 1, it truly gives me a canonically normalized, and this should be a pi hat field, but I'm sick of these pi hats. I'm not going to write pi hats. I'm going to forget about, now all the hats are, pi's are pi hats now, okay? All right? So this makes sense. This is now, if MQ was 0, I claim that the only things I could write would be terms that have more derivatives. This is the only term I can write with 2 derivatives. Because, for example, if I tried to write trace d mu sigma dagger, could I do that? Well, then I'd have to do something like trace sigma. I could try to write things like this, but these are 0 because the generators are traceless, okay? So you can't write anything at 2 derivative order. But at 4 derivative order, there's a whole bunch of things you could write. I'm not going to try to write all of them, okay? But here's an example of one. So according to my counting, it should have a coefficient of order f squared over lambda squared. And then I could write, for example, just the thing that I had before squared, the whole trace squared. And then I could write other things with strings of traces, blah, 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 okay? Okay? Plus some more things, okay? But now I also want to write down the terms that depend on the quark masses, okay? And so the lowest order term that I can write with the quark masses would be something like C prime f squared, lambda, so by dimensional analysis trace, MQ sigma dagger plus the Hermitian conjugate, right? Okay? Because this is invariant, and notice this has no derivatives, right? This has no derivatives. Okay, so if I don't have MQ, I can't write down anything that doesn't have derivatives, right? And so what that means is, since the theory without this term doesn't have any derivatives, right, then this thing here, this thing right here predicts that m pi and all the other ones are exactly 0, right? There's no mass term here because everything has at least two derivatives. Okay, so this has, if you expand it out, it has lots of interesting interactions that are actually experimentally probed as well, but focusing on the masses, they don't give you anything for the masses. But this gives you something for the masses, right? Okay, so in fact, what does it give you? Well, you can just expand this out, right? So you can say, okay, wait a minute. Sigma starts off with 1, but that just gives me a constant term. Okay, that's no problem. But then there's a linear term. Oh, no. But it turns out that that linear term vanishes too. And the reason is because it's complex, and I have to add the Hermitian conjugate here. So if I expand this thing out, the first thing that I get is like C lambda squared, okay, because each pi comes with a 1 over f, because remember that sigma is now this, okay, since I'm dropping the hats. So each power of pi comes with a 1 over, let me just write it this way, okay, pi squared over f squared, and 1 power of mq, and 1 power of lambda. Yes? Okay? And so the f's actually cancel, okay? This is not of order 4 pi. This is multiplied by pi squared, okay? So without even thinking, let's say all these quark masses were the same, they're of course not, okay, but just order of magnitude, what I'm getting here is that the mass of one of these mesons, like the pion, is of order, so because the whole idea of this power counting is that the C prime thing is supposed to be order 1, right? So this is supposed to be of order lambda QCD, 1 GeV times m quark, okay? All right, and so this is, you can see that this is much, much less than lambda QCD, right, if m quark is much, much less than lambda QCD, okay? So this is really cool, okay, for many reasons, okay? So if my topic was actually QCD, the next thing I would do is I would say, well, you know what? This is actually a matrix expression, right? Because there's actually this is a 3x3 matrix, and these are 3x3 matrices. So the real story is that this is, I'm getting a whole 3x3 matrix, okay, right? And which would look something like a trace of MQ with the matrix pi squared. Okay, so I'm getting something like lambda times some order 1 coefficient times this, okay? And so this is predicting 8 masses, 1, 2, 3, 4, 5, 8 masses, as I said, plus minus is 2. I think that's the point, right? 8 masses, some of which are identical by CPT, okay, fine. But anyway, you're getting, this thing gives you 8 masses, okay, in terms of 3 parameters, okay? And actually, how many independent ones are there? Let's actually count. These are the same by CPT. These are the same by CPT. 1, 2, 3, 4, 5. There's 5 of them that are actually different. So once I use CPT, there's only 5. But that means that there are 2 relations here, okay? And so these relations were written down by Gell-Mann just by saying that, hey, and maybe somebody, one of the other guys, it's always Gell-Mann and somebody, and I always forget who the other one was. But anyway, there are 2 predictions here, and these are these famous Gell-Mann somebody relations, okay? But what I'm really excited about here, what we care about here, is that, wait a minute, okay? These things are scalars. Let's remember, they're scalars, right? And the whole problem with the standard model is, how do I get a light scalar mass, right? And somehow QCD has done it for us. It's accomplished it, okay? So it behooves us to figure out, how did it do it? What's the trick? And once we understand the trick, can we just use that to explain why the Higgs is light? Okay, this is incredibly exciting, okay? And in fact, this is the idea, as you just heard me say just a few minutes ago, an hour ago, whatever, that this is the idea behind the Higgs is a pseudo-Nambu-Goldstone boson, because indeed, these things here, in the limit where they're exactly 0, they're Nambu-Goldstone bosons. But now, when I've turned on a small explicit breaking, they are pseudo-Nambu-Goldstone bosons. Okay. By the way, Nambu used to call them Goldstone bosons, and so did everybody else, actually. I heard, I've never heard him actually, I only met him once very briefly, but I heard that Feynman used to call Feynman diagrams my diagrams. But anyway. Okay. Okay, so we're going to talk about what is the secret sauce behind this. Well, how can we maybe generalize this? But let me just stop here. This is all I kind of wanted to say about this. Yes?
Okay, I'm thinking from a EFT perspective, but I guess that when you are expanding this trace of partial of sigma, you are obtaining different suppressive terms, right, of interaction between the pions.
So you're saying that if I'm including these higher terms here, yes.
Yeah, but not just those, also the terms that you obtain from expanding
also
this.
just, yeah, expanding these. So these terms really do look something like pi squared, you know, d pi, yeah, exactly, with an overall trace, right? And then there would be a 1 over, you know, f squared with some order 1 coefficient. This is what they would look like, yes.
Yeah, so at a certain point, they're going to mix, no? In terms of dimension, the terms from the first expansion and the terms from the second expansion, right? I don't know if I'm explaining myself well. I mean, you have one term that is trace of 2 sigmas, right?
Yes.
And then you can expand this at 2-dimension whatever. And
right.
then you can expand also this second term.
Right.
And at some point, they will mix in this. They will have terms that will have the same dimension, right?
Okay, yeah, so
they will mix.
Yeah, so you're kind of asking, there are many, you know, you can spend your life studying chiral perturbation theory. There are many things to say. You know, I think what you're asking is sort of, I think what you're asking is how does the low energy expansion here work? Okay, because it seems like this is already an infinite number of terms. Here's another infinity. How does it all organize? Okay, it actually organizes in a very simple way, okay? Because the simple observation is simply that no matter how many fields there are here, there are always 2 derivatives, okay? So these higher and higher terms, like this one here, is just literally a propagator. This term is a 2-point function. The next term would be a 6-point interaction, an 8-point interaction, and these ones would be, this one has a 1 over f squared, this one has a 1 over f to the 4th, and remember that apart from this factor of 4 pi, this f is a UV scale, right? And so these effects are higher and higher multiplicity terms, okay, that never stop, and they're suppressed by powers of f. This term here always has 4 derivatives, okay, so it starts off with this f squared over lambda squared, and then every time you add another pion, you add another 1 over f, okay? And so there's sort of a dual expansion in the number of derivatives and the number of pions, and each of them costs you. So this groups together all the terms with, not all of them, because there are even a few more operators, but these are the terms with 4 derivatives, these are the terms with 2 derivatives. And amazingly, all the higher multiplicity terms are determined, or completely determined, at 2 derivative level. At 4 derivative level, there's a few more parameters, so that's roughly how it works.
Okay. And then I guess that you can also apply one loop corrections and all that.
Yes, there's a whole story about the radiative stability of this thing. Okay, so actually one of the ways to derive or motivate this naive dimensional analysis, in fact the way that Georgi and Manohar originally did it, was to say that this ansatz is radiatively stable in the EFT. Okay, and the radiative stability is also discussed in a very nice paper by Weinberg. Back in the day when people thought that loops and EFTs don't make sense, you know, somebody had to show how that was done, and that was Weinberg who originally did that for this model.
Okay, that's all. Thank you.
Yeah.
Just following up, what do you mean radiatively stable?
Oh, what I mean is that if you, what I mean is that if you start computing loops, okay, and start correcting this Lagrangian, then it'll just change the numbers that are in this expansion by order 1, okay? So for example, there's a certain structure to the renormalization, okay? So this term doesn't renormalize that term, but this term renormalizes that term, but it just renormalizes it multiplicatively by logs. And there's some sort of cascade like that. Okay, the lower order terms only renormalize the higher order terms, not the other way around, and it's in such a way that this sort of power counting that I've done here is preserved. Okay? Yeah. And another way to think about it is that, yet another way to think about this is that the loops are actually becoming more and more important as you go towards the lambda QCD scale. And in the EFT, the loops at the scale when the energy is of order lambda, then the loop corrections are actually of order 1, but that matches what we expect from QCD, right? Where it makes sense that the EFT is getting strong when the fundamental theory from the top down is getting strong. So that's yet another way of motivating this. The real proof that this works is that if you match these numbers from experiment, they really are order 1. Okay, they really are like 1/2, 2, things like that, okay? That's the real proof that this works, but there are many reasons to expect that it should work.
Yeah, following up if you don't mind.
Yeah.
So when we had the massless quarks, we get the spontaneous symmetry breaking. Even when we have non-zero masses, we still get the spontaneous breaking, the fermion gets the wave.
Yeah, that's the picture that I showed. You know, you have the American tourist hat, and in the limit when MQ is 0, right, there's a whole manifold. I can't draw an SU3 on the board, but so I'm drawing a U1, okay, but there's a whole vacuum, SU3's worth of vacuum manifolds, and these are all exactly degenerate, but then, you know, you tilt it a little bit, right? The MQ is basically just adding some small tilt to this, okay? So it's that picture, right? So the idea is that as long as these excitations are well below the QCD scale, this tilting of the potential should be describable within the effective theory.
Okay, and just like in the Higgs, we had a potential and we could calculate the wave. So for this fermion, in this case, can you cook up some potential to get this wave?
Yeah, I mean, you know, usually what's done in these things is one sort of hides the fact that there's a VEV to be found because you just work in a basis where the VEV is always happening, where the fields vanish, okay? But technically, yeah, you're really minimizing a potential, and now when MQ is not equal to 0, there's a preferred point here where, you know, you live. Okay. In fact, that minimization becomes non-trivial if you have a QCD vacuum angle. Okay, that's another subject. I'm not sure how much detail I'm gonna go into the QCD vacuum angle, but I'm definitely going to talk about some aspects of it.
Okay, thank you.
Yeah. I mean, I remember when I was learning this stuff as a grad student, I actually thought, I don't know if I still think this, but I thought it's actually sort of profound that the vacuum selection is something that you can understand in the effective field theory, okay? And somehow the idea is that if MQ, which is the explicit breaking parameter over lambda, is sufficiently small, then you can think of this as sort of injecting some, you know, it's injecting some perturbation, but since it's a small perturbation, it can be described in the effective theory. I actually think that's kind of profound, but it works. Yeah.
There is something I missed at the beginning, and is when we have the mass term, this term breaks the chiral symmetry, but when we suppose the mass term goes to 0, which entity is breaking the symmetry in that case?
Yeah, then it's spontaneous breaking, right? So the idea was supposed to be that it's this quark condensate, okay, which I didn't explain, but I'm telling you that it's a fact that this is of order lambda cubed delta ij, okay? So this equation, you're supposed to understand it as if I was telling you that in the standard model, the Higgs VEV looks like this, okay? And in the standard model, you know how to calculate minimize the potential and show that this is in fact the lowest energy configuration, okay? In QCD, I certainly don't know how to do that, okay, but the claim is the same. The claim is that in QCD, the strong dynamics is such that the lowest energy configuration has a non-zero value for this fermion bilinear with this specific pattern, right? So this is a SU3 left cross SU3 right bilinear, right? And it's proportional to the identity, and this is spontaneously generated in the same way that the Higgs and the Bev in the standard model is generated.
Okay, thank you.
Yeah. Okay. Well, it looks like I'm efficiently burning a lecture here without getting to the end of my notes. Let me just say, I think I'm supposed to finish in 10 minutes, yes? Or am I already over? Ah, you can go up to 5:30. I don't know. Okay, let's see what happens. Let's see what people do, what people want. Okay, listen, I'm gonna finish something for a few minutes, and then I want you to think about this. We're gonna vote, okay? And I will leave the room, and you'll vote on whether you want me to go on for another half an hour or if you want to have a siesta. So I don't know who voted. I'll know the final count, but I won't know who voted, okay? Is that okay? Is that all right? Because I'm pretty tired, but I'm happy to go on, actually. It's just, it's real. I think you guys really should decide, because you might be totally sick of me at this point. Okay, so I want to learn, the main reason I'm interested in this here, okay, so first of all, you noticed, I hope, that this is an absolutely beautiful example of this sort of spurion philosophy, yes? Right? MQ, the whole thing came from treating the quark mass as a spurion, and I learned a lot, okay? All right? And so that's the first lesson, okay? And you're not going to be shocked that when we lift ourselves up to the rest of the standard model, we know that these quark masses came from Yukawa couplings, and guess what the Yukawa couplings are going to become? They're going to become spurions, and we're going to learn things, okay? So that's one lesson, is that spurions are good. This is another example. But then the other thing is I want to understand the basic mechanism by which we can get an arbitrarily small pion mass, right, by making the quark mass arbitrarily small, right? Whatever, I don't know how to write this, okay? And remember, the quark mass is a fermion mass, so it's perfectly natural to have it be as small as you want. Okay? It's perfectly natural. Okay? So this would be, if we could do this for the Higgs with no other consequences, we'd be done. Okay? Right? But then I wouldn't have given the colloquium the way I did. So, but anyway, let's understand what happened here. Why did this work? Okay? It's very simple. Okay? So let's look at e to the I pi prime of x. So now I'm going back to the dimensionless thing. Okay? So deal with it. All right, and what is this? This is e to some theta left transformation, e to the I pi of x, e to the minus I, some theta right, okay? So this is just rewriting the transformation law, okay? And so now what I'm going to do is I'm going to expand this perturbatively in both the parameters of the SU3 left and SU3 right, and also the pion fields, okay? So the first term I get over here is a 1, and I get a 1 over here. That's boring. I'm not going to write that. But the next term I get over here is pi prime, which remember is this matrix. And then I get a linear term in pi, right, where I set these equal to 1, and I get a linear term in pi. But I also get linear terms where I set this equal to 1, and I have the linear terms here. And so that gives me theta L minus theta R. Okay? And so, in other words, the pi field shifts. And then there are many, many higher order terms. It's more complicated than that. But the basic point is that pi shifts. Okay? And in hindsight, that's obvious, because remember, the picture is that it's like this. And guess what? You know, if I take an SU3 left cross SU3 right transformation, I go from here to here, that's precisely a shift in the pion. Okay, so I could have said this without writing any equations, okay, but you can also get it from equations. That's usually how it works, okay? So And you can just see from this, it doesn't really matter what the ... is, okay? You can see that this absolutely forbids me from writing just a pion mass term, something like trace pi squared, right? Trace pi squared by itself is obviously not invariant under this. Okay? Remember, these are all SU3 generator, Lie algebra elements, whatever. So that trace that would have a linear term. It would not be invariant. Okay? So the answer is we have found a symmetry that forbids a scalar mass, right? We should make the most of this that we possibly can, right? And indeed, there have been some, I don't know, probably, not as many papers as supersymmetry, but clearly hundreds, if not thousands of papers written on trying to make this idea work in the standard model. And I'm not going to review them all, okay? But I'm just going to tell you what this symmetry forbids trace pi squared, that we like that, okay? But it also forbids a lot of other things, okay? So notice that, for example, it also forbids a gauge coupling, okay? So d mu, if I wanted to make the pion charged, okay, it also forbids a gauge coupling, because this thing has a piece in it that looks like g squared a mu times pi squared. Okay? So now you might say, well, wait a minute. The pion is charged, okay? The kaon, there's a charged pion, charged kaon. Indeed, there is. And in fact, electromagnetism breaks the SU3 left cross SU3 right symmetry and also gives us additional contributions to the masses. For example, they split the K plus minus from the K0, and they split the K, they contribute to the splitting of these guys as well, okay? So there's a more complicated story there. But I don't want to focus on QCD. Here, I'm just trying to say that if we're trying to use this in the standard model, we have to be aware that this shift symmetry forbids something we don't want, but it also forbids things that we want, namely the gauge couplings and the Yukawa couplings, and that's the obstacle in just sort of porting this idea directly into the standard model, okay? Nonetheless, this is the basis of the PNGB Higgs mechanism. Okay, so I think that's it. And so, is it okay? Is it too gimmicky to do this vote thing?
No,
okay.
It's not okay.
So I'm just going to walk out with this thing.
No, I'm going to use my organizer power.
Oh.
Because I think I've done enough.
Okay.
And I think the other organizers agree that
okay.
You should get some rest.
No, I'm fine. I really think it's you guys I'm worried about. I'm serious. So.
You have 2 more lectures.
I have 2 more lectures. Okay, good.
So let's
All
thank
right.
Markus
Thank
for
you.
this colloquium and the lecture. But we still have time for questions, if that's okay.
Yeah, absolutely.
So questions for Markus.
So in KPT, this BEV in the condensate comes from a potential or something, but we don't know because it's non-perturbative QCD, or?
I would say it's a phenomenological input, okay? So, to put it in a sort of a grander perspective, what you can say is that, when you write an EFT, you should specify the symmetries and the particle content, okay? And conceptually, saying that we have this SU3 left cross SU3 right symmetry, spontaneously broken, and the MQ goes to 0 limit, right, down to this SU3 left plus right, I would put that in the category of defining the symmetries of the effective theory, okay? Just like if I told you that my Lagrangian had some U1 symmetry, whether that's true or not depends on the fundamental theory, right? The fundamental theory either gives me that symmetry or it doesn't. In the same way, QCD, this is either true or not true. There's an SU3 here. It doesn't break down to SU2, right? QCD either does this or it doesn't do this. It's an input from the fundamental theory that you need to know to be able to write the effective theory.
Okay, thank you.
Oh, just a second. I go there.
About the tilting of the Mexican head potential,
Yes.
is there an effect on the speed of this tilting? Like, is there anything about it?
Is there an effect? I'm not sure I understand the
Like
question.
the dynamics of tilting it being fast or slow during some dynamical process?
I'm sorry. The tilting is not a dynamical thing that happens. It's just that when MQ is equal to 0, the potential looks like this, and if MQ is not equal to 0, it looks like this. It's not that it's actually changing. It's not moving. I'm not sure if that's your question. It's just, you can think of this as being tilted, right? Because I'm not drawing it very well, but this is supposed to be lower than that. I mean, it's really the same as if I just had a symmetric potential and I just added a small linear term, like in the Ising model, or I have a magnetic field that biases me towards one of the vacua. If I just add a linear term, it's not literally tilting the potential. That's a little bit of a that's not literally correct. It's just adding a term that makes one of the vacua preferred.
Yeah, but I saw some things, not for QCD, but for axions, where the tilting happens like dynamic.
Well, I think they mean the same thing as this. I think it's just, it's not a very great language. I just used it without thinking about it because I hear it all the time too, I guess, in talks. But it's not literally tilting. It's just adding another term that it's just adding, it's basically sort of like this plus a little bit of that, and it's just making one of the vacua lower than the other.
Okay, thank you.
Any more questions? Yes.
Question is along the lines of the meaning / the goal that you're doing by doing this spurion analysis, in the sense that is this pseudo goldstone production, this symmetry breaking, like actually happening, or is it like a way of analyzing the effective theory? But if you take, for example, the QCD Lagrangian and you compute everything, all the loops and whatever, and you find the Bose-Goldstone, the pion states, then you compute the mass, you will get this even without this analysis, but this analysis just shows you that it should be this.
Yeah, you're asking me, is this all bullshit? Is that what you're asking me? No. So no. Yeah, I'm a total realist. Okay. So no. So for example, we in lattice QCD, you literally do an ab initio numerical approximation to the full QCD Lagrangian. Yes, and you indeed find. The way you actually get it, they can show that this is non-zero, that it has this pattern, okay? They can see that the pion is light. They can see that the pion obeys these relations that I've derived here. This is really true. That's the idea, okay? So so in the lattice, I know the computer knows how to calculate this, and it gets the answer that I said. Okay. This was discovered by, Nambu and other people because this worked phenomenologically, right? That's the way it was discovered. But then much later, now QCD calculations are really precise, and so they're able to confirm this in a way directly.
Okay. So this is a really useful way of seeing it, but you can actually compute it as well. Okay.
Yeah, I mean, it would still be a great theoretical problem. Can you somehow prove that this happens from using pencil and paper? Even if you can't compute this coefficient, can you show that this is non-zero using pencil and paper? That's an open problem.
Oh, okay. Okay, thank you.
Okay. I don't see any hands up, so let's thank Markus again. And so we have the